Electricity. You know, it's this invisible force that powers, well, pretty much everything in our modern lives. But have you ever stopped to think about how it actually works? Well, today we're going to break it all down, one simple idea at a time. So let's get right into it. Think about it. It all kicks off with something super simple, right? You just flip a switch and boom, the room is full of light. But what is really going on inside those wires to make that happen, like instantly? That's the invisible magic we're going to uncover today, step by step. Okay, to really get a handle on electricity, let's start with an analogy that everyone gets: water. I mean, we all know how a river flows, right? Well, that simple idea is the perfect way to start thinking about our first big concept: electric current. So just imagine this for a second. The wires in your walls, they're like pipes. And the electricity, that's the water flowing through them. Now, if you think about the amount of water that's moving past a specific spot every single second, well, that's it. That's our first key idea. That's the current. All right, let's put on our science hats for just a moment and get a little more technical. So, formally, electric current is the rate of flow of electric charge, and we measure this flow in a unit called amps, or just amps for short. Fun fact, it's named after the French scientist André-Marie Ampere. Now, here's the catch. For this current to actually go anywhere, it needs a complete unbroken path to travel on. We call this an electric circuit. You can kind of think of it like a racetrack, you know? You've got to have a power source, like a battery, to get the race started. You need a component, like a light bulb, that's going to use that power. And of course, you need the wires, the track itself, to connect everything together. And if there's any break in that path, say you open a switch, well, the race is over. Everything just
Okay, so we've got this flow, this current. But what's actually making it move in the first place? You know, going back to our water analogy, what's the pump that's pushing it all along? And that right there leads us straight to our next big idea. Right, so if you have water in a perfectly flat pipe, it's just going to sit there, isn't it? It's not going anywhere. To get it moving, you need some kind of pressure difference. Maybe you use a pump, or you just tilt one end of the pipe up. Well, believe it or not, the exact same thing is true for electric charges. They need a push. They're not going to move on their own.
And in the world of electricity, this push, this electric pressure, has a name: potential difference. But you probably know it by its much more common name: voltage. It's basically the energy that's supplied to get a charge moving from point A to point B. And it's what a battery provides. We measure it in volts. And the rule is simple: no voltage, no flow. End of story. So let's recap. We have the flow, which is the current. We have the push, which is the voltage. But what about stuff that gets in the way and slows things down? Well, that brings us to the final piece of our puzzle. Let's go back to our water pipe again. Now, imagine there's a section of that pipe that's super narrow, or maybe a little clogged up. The water can still squeeze through, right? But it's a lot harder. It's facing some serious opposition. Well, in an electric circuit, it's the same deal. Some materials and components create a very similar kind of obstacle for those flowing charges. And this opposition, this thing that fights against the flow of current, we call that resistance. It's just a property that materials have that makes it harder for charge to move through them. Pretty much everything has some resistance, and we measure it in a unit called ohms. All right, so there we have it, the big three. We've got current, that's the flow. We have voltage, that's the push, and we have resistance, the obstacle getting in the way. So how do these three things all relate to each other? Well, this is where a really, really simple but incredibly powerful rule comes into play. So let's take a quick trip back to 1827. A German physicist, George Simon Ohm, was messing around with this stuff and he discovered something fundamental. He figured out that for any given material, the push, the voltage, is directly connected to the flow, the current. It's a really clear relationship. And he boiled this whole relationship down to one beautifully simple little equation: V equals I times R. That's it. Voltage is just current multiplied by resistance. This is the famous Ohm's law, and honestly, it is the golden rule for understanding basic circuits. The coolest part? If you know any two of those things, you can always figure out the third. Okay, theory is great, but let's see this thing in action. Let's imagine we have two totally different devices. First, a light bulb with a really high resistance, about 1200 ohms. Then we've got an electric heater,
and its coil has a much lower resistance, only 100 ohms. Now, we plug both of them into the same 220-volt outlet. So, what do you think happens?
Well, if we use Ohm's law, the answer becomes super clear. The light bulb, with its super high resistance, only lets a tiny little trickle of current flow through it, just 0.18 amps. But the heater, with its low resistance, it lets a whole lot more current rush through, a full 2.2 amps. See, the push, the voltage is exactly the same, but the size of the obstacle totally changes how much flow you get.
And you know what? This whole idea of resistance, it's actually what separates different kinds of materials from each other. I mean, why do we use copper for the inside of a wire, but wrap it in plastic for safety? It all boils down to one thing: resistance.
Yeah, this massive difference between materials is all about a property we call resistivity. It's basically their built-in ability to fight against the current. Just look at these numbers. A fantastic conductor like silver has practically zero resistivity. It lets current flow like a champ. Then you have something like nichrome, the stuff in heaters. It puts up a decent fight. And then you've got glass, an insulator. I mean, its resistivity is so ridiculously astronomically high that it basically tells the current, "You shall not pass," and stops it cold. So this brings us to a really cool final thought. We started out by talking about resistance as just an obstacle, right? Something that gets in the way. But it turns out that very opposition is something we use every single day. The filament in a light bulb, it has super high resistance, and that's why it glows so brightly. The coils in your toaster, same deal. Their high resistance is what generates the heat to make your toast. So even though resistance slows down the flow, that friction is exactly what we've learned to turn into light and heat and pretty much all the tools of modern life. So I'll leave you with this question. Is resistance an obstacle?